Okay, so in the last few sessions, we talked about singly reinforced beam, wherein we provide reinforcement only on the tension side. In the last lecture, particularly, we learned about the analysis of singly reinforced beam, meaning that we know the dimensions of the beam, the amount of reinforcement, and then we back calculate the moment that it can carry, and hence the amount of load that we can put on the beam. And we just solved one numerical pertaining to under reinforced beams, and we saw how do we use all the equations and all the formulations that we studied, and how do we put them in actual practice. Okay, so we'll just end this with one more numerical, so that you also get a feel of what to do when we get over reinforced sections. So please write down an RCC beam. An RCC beam 300 by 600 mm overall in section, 300 by 600 mm overall in section, is reinforced with 8 bars of 25 mm diameter. Is reinforced with 8 bars of 25 mm diameter with a cover of 25 mm. With a cover of 25 mm. Calculate moment of resistance of the beam. Calculate moment of resistance of the beam. Consider the beam made of M30 concrete and Fe 550 steel. Consider the beam made of M30 concrete and Fe 550 steel. Okay, so the given data is the width of the beam is 300, the total depth is 600, then now it is reinforced with 8 bars. Now it seems a little practically difficult or almost impossible to fit in 8 bars in 25 mm diameter, but nonetheless this is what is given in the question without mentioning if the number of layers is 1, 2, because depending upon that our effective diameter changes. So I don't want to get into complications right now by giving 2 layers and then uh, changing the value of d. I'll just keep it simple right now. So just assume that all of them are fitted in one layer. So if 8 bars of 25, then just write down all the given data. Width is 300, depth is 600, AST is 8 bars of 25. Now the diameter of one 25 mm bar, which is 5 by 425 square, is approximately 490. And therefore 8 times 491, so this is approximately 3920. Or if you want an exact value, you could always just say pi by 4 t square, or you could just write an exact value here. So pi by 425 square is 490.87, and then times 8 is 3927. So this is AST. Then the grade of concrete is 30, the grade of steel is 550. Okay. Now what is given in the question is that the cover is 25 mm. Now whenever cover is mentioned without explicitly saying that it is clear cover or effective cover, we always assume that it is clear cover. So cover is equivalent to clear cover. If it is explicitly mentioned that it is effective cover, only then you consider whatever is the given value as d dash. Else you just consider it as the clear cover. So even here, the clear cover is 25. So like we have seen before, the effective cover is equal to clear cover plus stirrup diameter plus bar diameter by 2. So this is 25 for beams, 8. You can assume 8 to be the stirrup diameter, and this is 25. So this turns out to be 45.5. And then our effective depth is d minus d dash. D is 600, d dash is 45.5, and this is 554.5 mm. Okay, so like we did in the previous problem, since we do not have any idea about what the depth of neutral axis could be, and hence we do not know if the section is under reinforced, balanced, or over reinforced, we start with an assumption that the section is under reinforced. So for this assumption, by force equilibrium, we get Cu is equal to Du. When we equate these two, what we get is Xu is equal to 0.87 Fi AST upon 0.36 FCKB. AST is something that we have already calculated. So I'll just delete this from here. AST is something we've calculated here. So are you guys able to follow, or is it too fast?
You can go a little slow.
Okay. So I'll just wait here for a moment and let you write this down. So I just hope this portion is clear. Just about finding the effective depth. Okay. Then we move ahead to find the depth of neutral axis, which is 0.87 Fi AST. Our Fi is 550 and our AST is 3927. And then 0.36 FCK, which is 30 into B, which is 300. So I've just plugged in the values of Fi, AST, FCK, and B in the equation for XU. Can someone please calculate this value?
$579.9.
579.9. Okay, so this is our XU. Now, one thing that we have a value of XU. Now, the next step is to compare the value with XU max, and only then we can say if the section is under reinforced, then our assumption is true. Now, we have a set of values of XU max for different grades of steel. For Fe550, if I just go back to the page where we derived these values, so for Fe550, the value of XU max is 0.44D. Okay, just a quick revision. For 250, it is 0.53D, 415.48D, then 500.46D, and 550.44D. So 0.53, 0.48, 0.46, 0.44. So in this case, it will be 0.44 times of the effective depth. So XU max is equal to 0.44 times 554.5.
243.98.
243.9. Okay. Now, if we compare XU and XU max, what do we see?
XU max is greater than XU. No, XU max is less than XU.
Yes. So XU is greater than XU max, which means that the section is over reinforced section. Which means that the section is over reinforced. And therefore, our assumption is false and FST is less than 0.87 Fy. Okay, so a quick revision why this happens. If we talk about mild steel, let us take the example of mild steel. Now, the section is under reinforced. The section is over reinforced. Now, we know what happens in an over reinforced section. At the ultimate limit state, concrete strain reaches a value of 0.0035, but the strain in steel is still lesser than epsilon St star, which is 0.002 plus 0.87 Fy by Es, meaning that the steel has not yet yielded. So this is our yield point here. Our strain, if our strain is lesser than this value, our stress is also going to be lesser than this value, and hence the stress is going to be less than 0.87 Fy. Now, because of this, we do not know, there is no way of finding out what FST is. Of course, there's a way. What you could do is, you could start with an assumed value of XU and then just calculate everything, back calculate the value of XU like we did, and so on. So basically, it is an iterative process now. It does not have a closed form solution here. So, in examination, it is practically not possible to perform such an analysis wherein you do not know what is the stress in steel or what is the depth of neutral axis, or if the section is over reinforced. So what we do is, please write down the following statement after this. So what you can do is you can copy everything up to this point and then stop here. So please write down, since the section is over reinforced, since the section is over reinforced, FST is less than 0.87 Fy. FST is less than 0.87 Fy, and we do not get a closed form solution, and we do not get a closed form solution, full stop. XU will have to be computed. XU will have to be computed by strain compatibility. By strain compatibility method to get the actual moment of resistance. To get the actual moment of resistance. Now we do not need to get into what is strain compatibility and how it is done. So the procedure, the brief of the procedure is what I already told you. We just start with an assumption of value of XU, then we calculate all the terms, use the same equations to back calculate XU. If the first value and the last value matches, meaning that the value of XU that you started with is correct and you have got a closed form solution. And this is an iterative process. So it's practically not possible for us to get into the process, but then at least it's good for the invigilator to know that we are aware that it is an iterative process. It is going to require uh, it is going to require a number of iterations, and the method is called strain compatibility. So if the invigilator sort of gets a feel that okay, you're not actually doing the process, but you at least understand what the process is, then there's no need to go further. Please write down next. Since IS 456, since IS 456, 2000, since IS 456, 2000 does not allow the use of over-reinforced sections, does not allow the use of over-reinforced sections, MUR is equal to MUR is equal to MUR max. MUR is equal to MUR max. Okay, so this is the, even though in actual the moment capacity of the section might be greater than MUR, but since the section is over reinforced, we'll limit our MU to MUR max. So we know that the only difference between MUR and MUR max is when you substitute XU max in place of XU. So we can write it this way. So MUR max is equal to 0.36 FCK B into XU max, then D minus 0.42 times of XU max.
Bhargav,
Yeah.
Four will
when
Sorry.
yeah, sorry, 1 second. When when XU is XU max, we use the other formula, right? The last one, 0.87 FCK into AST into D minus 0.42 XU.
Just a moment. So okay. So when the moment of resistance is equal to limiting moment of resistance, that is MU max. Okay, if there's confusion because of this, what we could do is we could also write this as MUR max. So just please correct this in your notes from last lecture. Or just a moment, just let it be. I just corrected what we've been doing today. So please correct this. This is MU max. Let us represent limiting moment of resistance as MU max. So on to your question. As we saw it last time, the limiting moment of resistance is equal to 0.336 FCK B into XU max, D minus 0.42 times of XU max. The reason why we can use only this formula and not the other one is because we do not know the value of FST. FST is not equal to 0.87 Fy. Okay, had this been the case, it would mean that the section is either balanced or under reinforced, and we could just do our normal calculations. We did not have to limit our moment to MU max.
Okay, yeah, got it.
Okay. So our MU here is equal to MU max. That is when we replace XU by XU max. Now all the other terms remain the same. I'll just write it down again. So MU max is equal to 0.36 into FCK into B into XU max. Now XU max we've calculated is here 0.44 times of D, which is 234.98. So I just approximate it as 235 into depth, which is 554.5 minus 0.42 times XU max, which is 235.
Bhargav, it will come 0.44, right?
Sorry,
It will come 0.44, right?
what would be 0.44?
T minus 0.44
Okay, why would it be 0.44?
because we have the value for XU max as 0.44 D.
Oh, okay, okay. So this value is something that we have already calculated. So XU max 0.44D is something that we've already calculated to be 234.98, which I've approximated as 235. Okay, so this formula is different. This formula is our normal moment of resistance formula, 0.36 FCK B into XU. Okay, let me just go back a few slides. Yeah, so this is our formula, 0.36 FCK BXU D minus 0.42 times of XU. This has got nothing to do with if XU is greater than XU max or less than XU max. It has got nothing to do with that. This 0.42, this term is Z, which is the lever arm. So this 0.42 is different from 0.53, 0.48, 0.46, 0.44. That's different. This comes from here. X bar is equal to 0.42 times of XU, meaning that this X bar here is 0.42 times of XU, and therefore this is D bar minus 0.42 times of XU. So it has got nothing with the grade of steel. It has got nothing with the type of section. Okay.
Yeah.
Okay. So 0.42 times of 235. Can someone please give me an answer?
Three 347.04 into 10 to 6.
327
347
347
104.
0.04. Can someone please verify this?
Yeah, even I got the same answer.
Okay, so this is a Newton meter. Last time I explained you how to convert it into kilonewton meter. You just have to get rid of this value here. So it is 347.04 kilonewton meter. And therefore, your moment of resistance is 347.04 kilonewton meter. So it's actually easier if you get a over reinforced section.
Bhargav,
Yeah.
why didn't we use the 243.98 value for XU max?
Okay. So it is 254.98. Yes, you
Okay,
can
okay, we
use
rounded off. Okay.
yeah, just for the limitation of space and uh, no need for that much accuracy. I've just gotten rid of the two decimal places. Okay, any questions here?
Bhargav,
Yeah.
the value for XU max is coming as 244 and instead of 234.
Yeah, it wasn't 234, it is 243.
243. Okay.
Yeah.
So now we're gonna have a correction here. 0.44 times by 0.5. Yes. So it is 243.98. Okay, so this I can approximate as 244. Please correct this. 244 and then correct this value accordingly. 0.36, 30, 300, 244, 554.5 minus 0.42 times of 244. So this would be 357.35. Can someone please verify this value?
Yeah, it's correct.
Like, okay. 357.35. Okay. There's no need for this step since it is not asked. Okay, that's it. The problem is that simple and that small.
I had a question not
Yeah.
related to numerical.
Sorry.
Okay, would we prefer like two reinforcement of a specific area or four reinforcement evenly divided? Like both of them are balanced, but two rods or four rods with same area.
Could you please ask that question again?
Yeah, for example, there are like four reinforcement going through this.
Yeah.
Instead of that, with the same area, we insert two reinforcement with a greater radius. So which one is preferred?
Okay. Okay. So there are two things here. First is that irrespective of what the diameter of the reinforcement is, one thing it is to be ensured that there's adequate gap between two bars so that concrete can go in. That's the first thing. Okay. And after you satisfy this, keep the radius of the bars as minimum as possible. Because what happens is there's something called as development length. Development length is related to the bond of concrete and steel. So it is the length of the bar that is to be embedded in concrete so that there can be a unified action. Okay, to explain it in very simple terms. So imagine this to be a concrete block. Okay, and imagine that you sort of inserted a rod before casting the concrete. So this is the length of embedment. Okay, so this length, just a minute. Yeah, so this length is a function of this length which is required to develop a full stress in the bar, which is 0.87 Fy. So this length is a function of the diameter of the bar. Larger the diameter, larger the diameter, larger is the length of embedment, meaning that you'll have to insert it backwards further. Okay, so it is always preferred to have as lesser diameter as possible. But if it is leading to congestion, then definitely we sort of reduce the number of bars, increase the diameter, and then make sure that this LD requirement is satisfied or the length requirement is satisfied.
Okay, thank you.
Okay. Any more questions? Okay. So after this, we jump to what are called as doubly reinforced sections. Okay, please write down next heading, analysis of doubly reinforced sections. Okay, I think we briefly discussed it in the last lecture. Uh, Someone even had asked a question about using reinforcement even in the compression zone, since uh, steel is not only strong in tension but also strong in compression. And then the answer to it was doubly reinforced section. Does someone recall why do we use or when do we use doubly reinforced sections?
In a earthquake prone zone,
Earthquake
or
prone zone.
like, so like the load is uncertain, like
Okay, so
which may
you're
change.
yes, your answer is correct. We use it in seismic zones. We use it when we design beams, which are a part of the lateral load resisting system. That is because the load can either be from one direction or the other. So your steel, so there's something called a stress reversal in a beam. You're not certain that the sagging moment will always be at the center and the hogging moment will always be at the supports. Or you have to put it in other words, you cannot be sure that you will always require tension reinforcement at the bottom of the beam. You might also require it in the top at the center. So the so this particular answer has a very specific application. Okay. So in general, in gravity design, when do we use doubly reinforced beams?
When we absolutely don't have any space for larger beams.
Yes. So, uh, like I said in the last lecture, when the depth of the beam that is being provided is not sufficient to carry the load, in that case, we always have an option of providing reinforcement even in the compression zone. What happens because of that is the moment of resistance of the beam increases while the beam is still under reinforced. Okay, but yes, there are a lot of calculations behind how much to put and where to put, and we are going to get into these calculations in a while. Okay, please write down. Normally, normally, steel is provided in concrete beams. Normally, steel is provided in concrete beams to resist tension. To resist tension. But but it has been observed in the previous section. It has been observed in the previous section that a singly reinforced section that a singly reinforced section can offer only a limited moment of resistance. Can offer only a limited moment of resistance. In brackets, you can write mu max. Mu max. On many occasions, on many occasions, under varied conditions, under varied conditions, the size of a concrete beam, the size of a concrete beam has to be restricted, has to be restricted due to architectural and practical requirements. Due to architectural and practical requirements. but the same section, comma, but the same section, but the same section is required to resist a moment, is required to resist a moment greater than mu max, greater than mu max. In such cases, in such cases, additional moment of resistance, additional moment of resistance is obtained by adding steel, is obtained by adding steel on both tension and compression sides, on both tension and compression sides. Such a section is called as doubly reinforced section. Such a section is called as doubly reinforced section. So just to summarize what we just wrote down, a singly reinforced section has an upper limit for MUR, and this MUR is equal to MU max. Okay, now if we increase the amount of reinforcement here, we can sure attain a value which is greater than mu max, but it is not permitted because in that case our section will be over reinforced section. So we don't have, let's say that we have already exhausted all our capacity and then we don't have an option of adding reinforcement on the tension side. And either because of loading or because of the span, say the moment demand is greater than mu max. In that case, what we do is we add reinforcement here, but at the same time we also add reinforcement here, which increases the moment capacity, and at the same time we make sure we add steel in such a way that the section still remains under reinforced. Okay, now how is something that we're going to look at now. Okay, so just give me a moment. I'll just draw a quick sketch. Okay, so consider this section which has some amount of reinforcement on the tension side and some amount of reinforcement in the compression side. So let us denote this steel as AST, or area of steel in tension. Similarly, let us denote this as ASC, or area of steel in compression. So now we have to analyze this section. Okay, so an easier way to analyze this section is to look at it as a combination of two sections. So we can look at this section as a combination of a singly reinforced section which sort of has tension steel which is equal to AST max, or instead of that, let us just try to just make it, let's just keep it simple. Say just AST1. Okay, so this is equal to this plus a section that has AST2 and only ASC. There's no concrete. Okay, so we are looking at this section as a combination of a singly reinforced section with concrete resisting all the compression force, which is balanced by some amount of steel, say AST1, plus an imaginary section consisting of compression steel and tension steel, say AST2. So since this section is imaginary, perhaps you can just use okay. Now just some important parameters. This is XU, depth of neutral axis. Then this is effective depth. And this from the center to the top, this is D dash for the effective cover. Now since this is D dash, the distance between the compression reinforcement and the tension reinforcement is equal to D minus D dash. Please write down a doubly reinforced section, or you can just write DRS. A doubly reinforced section may be looked upon as two sections 1 and 2, as two sections 1 and 2 given below. Please write on the next line. Section 1. Section 1. A singly reinforced section. A singly reinforced section with concrete resisting compression Cu with concrete resisting compression CUC with concrete resisting compression CUC balanced by tensile force TU1 balanced by tensile force TU1 provided by tension steel AST1 provided by tension steel AST1. Please write down in the next line. Section 2. Section 2, which is an imaginary section. An imaginary section consisting of compression steel. Consisting of compression steel consisting of compression steel providing additional compression force providing additional compressive force CUS which is balanced by tensile force TU2 tensile force TU2 provided by tension steel AST2 provided by tension steel AST2. Please note that all these US, U2, AST2, all these are in the suffix. So I'll just repeat. Section 1, a singly reinforced section with concrete resisting compression CUC balanced by tensile force TU1 provided by tension steel AST1. Section 2 is an imaginary section consisting of compression steel providing additional compressive force US which is balanced by tensile force TU2 provided by tension steel AST2. Okay, might sound like a lot of variables and a lot of parameters at the start, but the overall idea is very simple. Okay, we have just split one section into two sections. In the first section, we are considering all the concrete and we are considering all the steel that is required to resist the compressive to generate a tensile force in steel which is equivalent to the compressive force in concrete. So this is the kind of section that we have studied until now. The second section is wherein you are considering only the compression steel. So we can split it in such a way. Initially we had Cu, which was, now we have split it into say Cu concrete plus Cu steel. Okay, so this is Cu concrete. So that is what we have written in the first section. So concrete resists CUC and this steel resists TU1. Compression steel resists CUS and the steel that is corresponding to the compression steel resists TU2. Okay, so our total compressive force is equal to CUC plus CUS and our total tensile force, that is TU, is equal to TU1 plus TU2. Okay, any question in this?
So here
Hello, Bhargav.
CO2 is only corresponding to the compression in steel, right?
Okay, so all T is tension. Okay, so what we have done is we have just split AST into AST1 and AST2. Okay, now how to do it is another question. Okay, let us just first understand the conception. We have split AST into AST1 and AST2. Now, AST2 balances out with concrete. AST1 balances out with only concrete, and the remaining steel, AST2, which is AST minus AST1, the remaining steel balances out with compression steel only. Okay, so the force, the tensile force in AST1, let us say TU1, the tensile force in AST2, let us say TU2. Total tensile force is TU1 plus TU2. Both of them are tension. The compressive force in concrete, let us say CUC. CUC. So C stands for compression, U stands for ultimate, and C stands for concrete. The compression force in steel, which is CUS. C stands for compression, U stands for ultimate, S stands for steel. So the total compressive force is CUC plus CUS. Okay? Just understand this splitting, that's it. How to do it and assumptions while doing it, that's another question. Okay, just splitting. Now we're just dividing it. Okay? Now we have divided it. Let us learn how to analyze it. Okay?
Hello.
Yeah.
Bhargav, won't the distance between the reinforcement be d minus 2d dash? Because there are like they
Okay.
are there
So
on both sides.
if I had written capital D here, okay, let me
Oh
write
yeah,
it.
because it's a small d.
Yes, because
Yeah,
this is
got it.
small d already.
Yeah, yeah.
Okay. So the same. Yeah. So this is the section that we've got for analysis. As before, we would consider the strain variation. The maximum strain in tension steel is epsilon ST at the ultimate limit state. The maximum compressive strain is 0.0035. Okay. Here we have an additional level at which we'll have to consider our strains, which is the level of compression steel. Okay. So let us assume that let us denote this by epsilon. Okay, so this is epsilon SC, meaning that the strain in steel in compression. Epsilon ST means strain in steel in tension. Epsilon CU means strain in concrete at ultimate limit state, which is 0.0035. Okay, clear? Now, when we look at I'll just draw it first and then I'll explain. So these are our strain, this is our strain variation. So these are our strains. Now we have to draw the corresponding stresses. So these are our stresses. Now for concrete, we know that the stress variation is something like this. Parabola up to a certain depth, then a rectangle. The maximum value is 0.447 FCK. We have approximated to 0.45 FCK. Then there's stress in steel in tension at this level. Similar to this, we are going to have stress in steel in compression. Okay, steel is in tensionless compression. Therefore, we'll have two stresses. One is a stress in steel in tension. Another one is a stress in steel in compression. Now, if I just draw the forces, so this force is CUS. We define it here, CUS. It is the compressive force in steel. This force is TU, the total tensile force. Then we'll have one more component, that is our compressive force in concrete, which we have seen that which acts somewhere here. So this is CUC. Okay, so just to remind you, we computed this distance as 0.42 times of XU. So I've just approximately drawn this here. So these are all our forces. This is the compressive force in steel. This is the compressive force in concrete, and this is the total tensile force. Okay. Now, if we look at the lever arms, we know that the lever arm between the tensile force and the compressive force in concrete is D minus X bar, which is D minus 0.42 times of XU. And just now, we've seen that this distance is D minus D dash. Okay.
Bhargav, just give us a minute to copy it now.
Yeah. Okay, so just quickly review what we have done. we know a section that has steel on the tension side and on the compression side. We have drawn the strain variation at the ultimate limit state. We know that epsilon Cu is going to be 0.0035. This is epsilon St and this is epsilon Sc. That is the strain in steel and compression. From strains, we can draw stresses. We know that corresponding to a strain of 0.0035, the stress is 0.45 FCK. So this is our FCK. This is the variation of stress in steel in compression. The stress is 0 here and a maximum value of 0.45 FCK at the extreme compression fiber. Since the strain at all these rebars is the same, the stress is also going to be the same, which is FST, and therefore there's only one arrow here. There is no area variation of the or there is no area on which the stress acts. It's just a small point. Similarly, the strain at all these compression or the strain in all these rebars on the compression side is also the same, epsilon Sc, and hence these will have the same value of stress, which is FSC. When we multiply FSC by area of compression steel, we get CUS. We already know how do we find out the value of compressive force in concrete, which is CUC, and we also know how to get TU from FST. The lever arm between TU and CUC is D minus 0.42 times of XU, and the lever arm between TU and CUS is D minus D dash. Okay? Great. Okay, so like we did in the analysis of singly reinforced beam, so the first step is that we try to find out what is the strain in steel and compression. So herein we consider similar triangles. From these similar triangles, perhaps I just write this again to avoid any confusion. So from these similar triangles, epsilon Sc upon epsilon Cu just look at this. So epsilon Sc upon epsilon Cu. Okay. So what should this be equal to? Show you to again. Epsilon Sc upon epsilon Cu. Meaning that we are considering these two rectangles, these two triangles. The first one is this smaller one, and the second one is this. So what should be epsilon Sc upon epsilon Cu?
It will be XU minus D dash upon XU.
Yes, correct. So this should be Xu minus D dash on Xu. Okay, which means that epsilon Sc is equal to Xu minus D dash upon Xu into epsilon Cu. Okay, We already know the value of epsilon Cu. This value is 0.0035. Okay, simple, similar triangles. Now, phi force equilibrium you know that the compression in concrete plus the compression in steel is equal to the total tensile force, out of which we already know what is the compression carried by concrete, which is 0.36 FCK B into XU. Okay, then what is the compression carried by steel? This is equal to the stress in steel, which is FSC, times the area of steel and compression. Okay, now we have to remove a small term here. I just write this down. See if you can understand this term and why is it that I've removed this term, and then we'll take the next step. 0.45 into FCK into ASC. So what I've written CUS as, it is equal to the stress in steel in compression multiplied by its area minus 0.45 FCK ASC.
Can you explain it once again?
Yeah, I've not explained it yet. So this is just something that I want you to see and try to understand as to why do you think there's an additional term here. Okay, so this additional term is there to account for the fact that while calculating CUC, we have, let me do it in different color. Okay, so ideally, while while calculating CUC, we should have considered the green area minus the red area. Okay, because there's no concrete there. But since we do not want to complicate the formula, we just kept it as it is. Let's say 0.36 FCK BXU. Do you understand this? Do you understand this? Then let's go on to the next step.
Yeah.
Okay.
Understood.
Yeah. So we should have subtracted this red area because that there is no concrete there. Okay. But this formula is it's already with a lot of difficulty that we with a lot of formulations that we have come to this formula. So we did not disturb this formula. What we did is we compensated that area of steel that we had considered by multiplying it by the corresponding stress, which is 0.45 FCK. Okay, so just a minute. So this rebar, actually, the force in this rebar, let us say CUS is equal to stress times area. The stress is FSC times the area is ASC. Okay, But since we did not remove this area from concrete, we have to compensate for that. What is the area? The area is ASC. What is the stress? The stress in concrete there is 0.45 FCK. So this is the stress, this is the area. And therefore we have a term 0.45 FCK and ASC. Okay, if we want to keep it simple, what we can do is we can just get rid of this. It won't make a lot of difference in calculations. Okay, because the area is very small, 0.45 CK times a small area is not going to make a lot of difference. Okay, so I leave it up to you. Do you want to do the exact calculations or do you want to get rid of this and make an approximation? Do you want me to explain it again and after that you want to give an answer?
Yeah, can you explain it again?
Yeah, okay. So there are two forces here. One is CUC and one is CUS. Okay. So
Just the last
actually,
part. Why would we subtract 0.45 FCKs?
okay. So when we calculate CUC, we consider the entire area B times XU. We do not deduct anything to account for the fact that some area is occupied by steel and not by concrete. Okay, this formulation is meant for a rectangular section, and that is why we do not disturb it. We keep this formulation the same. Okay, now we have to find out what is the compressive force in steel. Okay, for that, ideally, it should have been FSC into ASC. But because we also considered this red area as concrete, now we have to sort of subtract the force that is carried by the concrete in this red area. That force is equal to stress into area. We are deducting the force in concrete. Okay, so the force in concrete in this area is equal to the stress in concrete minus area of concrete. The force in concrete, the stress in concrete is 0.45 FCK. We can say that this stress is 0.45 FCK because your rebar is located close to the compressive axis, and therefore you might just assume that okay, this is in this area. So the stress in concrete is 0.45 FCK. What is the area of concrete? It is equal to the area of steel in compression, which is this red area. So we'll have to subtract this from here. And that therefore we have an additional term of 0.45 FCK into ASC here. So this is the force which is carried by force. So this is the force that is carried by steel, and this is the force that we have to deduct for concrete. Okay, so should we keep the term as it is or should we approximate it?
Bhargav,
Yeah,
TOS is ultimate compressive strength in steel, right?
yeah.
Okay, but so why are we subtracting it then? Because those three rebars are only the ones which are giving the compressive strength by steel. Like those three steel bars are only giving the compressive strength, right?
Yes, they are.
So then why are we subtracting it? Because don't we need that only?
Just a minute. Just a minute. Yeah. Actually, we are not subtracting it. Okay. In order to avoid any confusion, the first thing that we'll do is we'll get rid of this term here. It is not going to make a lot of difference. It will be 5-6 kilonewton here and there. Okay, so let us just get rid of this term.
Bhargav,
What?
sorry to interrupt, but we have a
Yeah.
lecture right now at 4:30. I mean at 2:30.
Okay, but we haven't finished our slot of 100 minutes. Can can it wait for 10 minutes?
I'll have to check with the faculty.
Yes. Parth, are you there?
Yeah, I just text the faculty about it.
Yeah.
Continue.
Yeah. So just to simplify things, the first thing that we'll do is just get rid of this. And just look at it. So this seems simple. CUC is 0.36 FCK BXU and CUS is FSC into ASC. Okay. And then our TU is equal to FST into AST. Okay. So if we consider force equilibrium here, what we get is so 0.36 FCK B XU is equal to plus FSC into ASC is equal to FST into AST. Just plugged in the values for CUC, CUS, and TU. Okay, so from this we can obtain the value of XU by just rearranging these terms. So XU,
Sorry, can you repeat the last step?
which this step, so I've just plugged in the values of CUC and CUS and TU in the force equilibrium equation. Okay. So with this, I can rewrite XU as so XU is equal to FST into AST minus, I can take this term on the left side, therefore this plus becomes minus FSC into ASC and then the left out term, which is this, gets to the denominator. This is equal to 0.36 into FCK into B. So this is a formulation for XU. So what we had before in singly reinforced beam is only this portion. In W reinforced we have FST AST minus FSC into ASC upon 0.36 FCK B. Okay, Now the question still remains as to what is the value of FST and what is the value of FSC. For a singly reinforced beam, FST, for a singly reinforced under reinforced beam, FST was equal to 0.87 F1. For doubly reinforced beam, we did not know that value. Okay. Now here, instead of one stress value of steel, we have two values, that is FST and FSC. Please write down. The equation provides a closed form solution, only if FST is equal to 0.87 Fy am I audible?
Yeah.
Yeah. So we're writing the equation provides a closed form solution only if FST is equal to 0.87 Fy and FSC is equal to 0.87 Fy. If not, then perhaps we won't be able to solve it in one go. We'll have to keep iterating. Path, did you have a talk with the concerned faculty?
Oh yeah, I informed them like we'll join by 2:45. So
Okay, great, thank you. Yeah. Okay, so our final output, that is the ultimate moment of resistance, MUR. We're going to have two terms here.
Bhargav, your screen is not visible. You're not sharing anymore.
Okay. So MUR is equal to CUC. Can you see it now?
Yeah.
Yes.
Yeah. So CUC into the corresponding lever arm, which is D minus 0.42 times of XU. And we'll have another term, which is because of steel, which is CUS, and the corresponding lever arm is D minus D dash. So if we just plug in the values that we already know, MUR is equal to 0.36 into FCK into B into XU into D minus 0.42 times of XU. This is a term that we already know. The next term is FSC into ASC into the corresponding lever arm, which is equal to D minus D dash. So this is what we finally require. You're already familiar with this term, only this is an addition. Okay, so with this we have finished the theoretical portion for the behavior and design of beams in flexure. We'll just solve a small numerical in the class in the next time for doubly reinforced beam, and then we are good to go for the next topic. Parth, can you please stop recording?
Yeah.